So good morning, everyone. I'm Richard Jones from Monash University down in Australia. And we've seen lots of great talks and posters so far this week about how the Antarctic ice sheet changed during the Holocene. And I'm going to try and build on some of those and a lot of other work, I should say, to kind of try and tell a story of actually what was the kind of complete ice volume change over the Holocene. And try and actually put some estimates to these volumes. Now, there's various reasons we might want to look into the geological past, and particularly the recent geological past of the Holocene. So first of all, we can do this to provide insights into processes on centennial, millennial timescales. We can provide bounds on possible rates and magnitudes of ice loss and ice gain. And we can try and provide this natural baseline to then be able to assess current and future ice sheet change. So let's start with the context of sea level. So what I'm showing here, rates of global mean sea level. In black is the global total, in red is the Antarctic specific contribution. And this is for the Holocene, the last century, and then into the future. So if we first of all look at this, the kind of historical sea level, Antarctica's contribution has been fairly small so far. But then we look at projections into the future, and the rates of change are going to dramatically increase, as we're all aware. The rates of this increase is going to depend on, obviously, the emission scenario and also what ice sheet processes we include in the models. So the pale shade there are those risk-averse projections. If we then look to the Holocene, we can see in the earlier part of the Holocene, we have these high rates of global mean sea level rise that's possibly similar to what we're going to be seeing towards the end of this century. And then we look to the later part of the Holocene, and this is fairly stable. It's kind of this baseline that current sea level change is assessed against. But it's been quite difficult to actually gauge what Antarctica's contribution is to this to the global sea level through the Holocene, and which warranted some further investigation. So we can actually get a better idea of how the Antarctic ice sheet changed through various different types of records from at the ice divide out to the continental shelf edge. What I'm showing here are the most kind of direct records that we have on the configuration of the ice sheet. So we have ice cores we can use, and glacial deposits on nunataks at the glacier margins to provide an indication of ice thickness change. We have seafloor sediment cores, and we've also heard about other subglacial cores that can try and constrain the grounding line migration. And then we also have lots of different types of coastal records recording loading, unloading, that give us an indication of regional ice mass change. So we compiled all this information to try and map out what the current state of knowledge is for the Antarctic ice sheet during the Holocene. And this includes kind of the magnitude of change and our level of understanding for each of the different sectors. Now, this is pretty busy, so I don't expect you to kind of digest all of that. I'm going to quickly summarize, and this is basically my conclusions halfway through. In the early to mid-Holocene, we see lots of evidence for rapid ice loss, and this is occurring in every sector of Antarctica. It seems to be slightly asynchronous between sectors, but there is generally this period where we see lots of rapid ice loss, and we saw from Yusuke and Keir on Monday more about that. We then see this period of ice sheet re-advance into the late Holocene, which is, there's some evidence in at least two sectors. And then the current Holocene ice sheet geometry, or the current present-day ice sheet geometry, was probably reached broadly by the late Holocene, but there are some patches around Antarctica where there's evidence that this continued kind of up to and into the industrial era. Now, all of these changes are driven by a whole combination of different factors. So there's a link of the rapid ice loss to incursions of circumpolar deep water onto the shelf, particularly in the Amundsen Sea sector, but also in other parts of Antarctica. There's evidence that actually the Northern Hemisphere ice loss and the corresponding sea level forcing actually possibly accelerated some of this ice loss in the early to mid-Holocene. There's evidence that actually the rate of retreat and ice loss has been kind of controlled, so it's kind of accelerated but also slowed down by bed topography, such as retrograde slopes and pinning points. Glacier isostatic adjustment has been linked to the re-advance, as we heard from Dan yesterday, but that's still kind of an area of work, and as Dan was showing, that actually oceanic changes perhaps had a more of a major role there. And then various other changes have been linked to different types of atmospheric change. But this is all an active field, and I think that our understanding and particularly the relative roles of each of these processes on Holocene ice sheet change is still kind of an area that requires active research. Now, if you want to kind of read more about the general picture of how the Antarctic ice sheet changed over this time and what we think are the main drivers, I encourage you to look at this review paper that came out last year. For the rest of this talk, I'm going to be looking at the modeled estimates, so how these models are making use of the constraints we have to try and give us this continuous record of ice volume change. What I'm showing here is the grounded mass loss as a mean from 11 different published models and colored by the different sectors. And first of all, you can see that actually here in the earlier part of the Holocene, we have these rapid periods of ice loss that are captured in the models. But actually, the majority of these models don't actually capture the timing correctly. So the evidence suggests that this probably happened at least a couple of thousand years later in most of the sectors. We also see where we get to this area of kind of more of a stable ice sheet with some parts of mass gain, and particularly in the Weddell and Ross Sea sectors. But yeah, there's still kind of an area where maybe this isn't as much as what the current evidence suggests. So how does all of this link into sea level contribution? So I've divided this here at 6.7 thousand years. And the reason for that is that this is when ice sheets in the northern hemisphere ceased retreating. So before this time, these models suggest that Antarctica contributed somewhere between 2.4 and 6.9 meters. And after this time, Antarctica should have been the main contributor to sea level change. And the model suggests somewhere between minus 0.2 and plus 5.3. These is quite a large range estimates based on these models. So part of the reason for this is this uncertainty between the various different models, which I've kind of displayed here in space. And so I think what probably jumps out most by the colors here is that actually in the earlier part of the Holocene, most of the uncertainty between the models is in the large embayments. And actually most of that is occurring in the deeper parts of those embayments. But actually the late Holocene is probably the most interesting, even though it seems like there's less going on here, because this is where some models are saying there's ice loss, some are saying that there's ice gain, and this is the period where we actually have least evidence to constrain the models. And we've heard quite a bit about that already, possibly because that evidence is buried beneath the ice sheet. This is also particularly important because this is the time leading right up to where we are today, and so we really need to understand this. And I thought I'd put this statement up from the IPCC to remind us that actually we still have limited evidence that there's a human influence on current ice sheet mass loss. And a big role, I think, we in the Holocene community is to try and actually provide better constraint of this natural baseline to be able to say whether we've moved beyond that or not. And so one way that we can actually improve our estimates of Holocene ice loss is to go to global sea level records. So beyond the Antarctic space here, what I'm showing here is a sea level fingerprint with the blue colors being sea level rise that corresponds to that ice loss in the early to mid Holocene. And then this is the kind of pattern of sea level fall that we see as a result of that simulated ice gain in the late Holocene. So you can see that the global sea level is basically dictated by what's happening in Antarctica. And there are so many relative sea level records from around the globe that we can use to then constrain these sorts of fingerprints. And so by then making use of this data, so assessing our Antarctic models against global sea level records, and then combining that with constraints against our local evidence in Antarctica, we can then get new estimates of global mean sea level and Antarctica's contribution to global mean sea level. I'm not going to talk any more about this because this is all Roger's work, so if you haven't seen this poster already, I encourage you to go to that. But we can also take this a bit further and actually provide sector-scale estimates using this approach. And so this is actually the revised model estimates of what we have of ice volume change through the Holocene. And what I think one of the main things that jumps out is that actually these periods of rapid ice loss here, in the previous models were occurring here, and now with this approach, we're able to better replicate the timing and the evidence. But also, there's a lot more mass gain that we see through the late Holocene, particularly in the Weddell and Ross Sea sectors. So now we have a better baseline, I would say, more confident baseline on how the Antarctic ice sheet changed, particularly in the later part of the Holocene. So perhaps we can now, we're now in a position to better assess whether we have gone beyond what we saw in the Holocene. But this is work in progress, so stay tuned for the full results. And with those inconclusive conclusions, I'll take any questions.
Great, so we have time for one quick question.
Nice talk, Rich. So it's the models are significantly under predicting the mass gain in the late Holocene, is my understanding from what you're saying. Have you had any discussions about why that is?
No. I mean, I think it depends on the models that are used here. I think the full ensemble that I say full ensemble, the 11 mean published models, I don't think necessarily that a lot of those were quite early models that weren't necessarily even considering that there would be this mass gain and any sort of re-advance. And the latest thing that I showed is basically a full ensemble of like 280 models from Thorsten Albrecht that has a whole suite of different models. So I think there's just generally been partly it's just a development in the models that is now capturing this process a little bit better. And as long as those models exist, it doesn't necessarily matter what the the underlying physics were and the forcings for that. If we're then able to test it against the evidence, we can at least then say these models are the ones that seem to best fit and therefore provide the most reliable estimates. But I suppose just to finish is that, yeah, even though we think we now have a better estimate of the late Holocene ice gain, particularly in those sectors, we still have very little evidence to test these models. So all this talk we've had about getting more evidence from beneath the ice sheet, I think is crucial to be able to test this further.
Fantastic. So we look forward to finding out more about your work in the future. So, Rebecca?